Hello, this is the section 5.8 lesson. In this section we're going to talk about another type of hypothesis test called a test of independence. Now at first glance this test is going to look completely different than what we did in section 5.7, but there's actually a lot of similarities. The test statistic is calculated in an almost identical way, and the underlying theory is very similar. So to illustrate this test, let's look at this example. Two students want to determine if their university men's basketball team benefits from home court advantage. And so they went out and they randomly selected 205 games played by the team and recorded if each one was played at home or away and if the team was won or lost. And this is some real data collected by a couple of students of mine a few years ago. And so here's the data that they collected. And so we see here we have a total of 205 games overall. 85 of those games were played at home, 120 were played away, 113 were a win, 92 were a loss. Now these middle numbers, for instance, tell us that 55 games were a home win, 30 games were a home loss, 58 games were an away win, and 62 were an away loss. Now this table is what's generically called a contingency table. So here's the data that we have collected. Now let's start setting up the hypothesis test, and then we'll talk a little bit more about the details of it. So the first step of a hypothesis test is to define the parameters and state the hypotheses. Now in this particular hypothesis test, we're actually not going to define any parameters. This is about the only test where we don't define parameters. And our hypotheses are going to look a little bit different than what we've seen before. Our hypotheses are not going to contain any numbers or any equal signs or not equal to signs or anything. The null hypothesis, as we've stated before, is a statement of the status quo. It's what we might expect to be true if we didn't have any data to indicate otherwise. So we might just think that, well, there really isn't any relationship between the result, either win or loss, and the location, either home or away. So in mathematical notation, that status quo is that the result is independent of location. Remember, the idea of independence back from chapters 1 and 2 means that there's no relationship. So that's going to be our null hypothesis, that the result is independent of location. Now the alternative hypothesis is going to be the opposite of the null hypothesis. The opposite of independence is dependence. So our alternative is that the result is dependent of location. Now we could alternately state these hypotheses in maybe less technical terms. If result is independent of location, that means that there is no home court advantage. And if they are dependent, well, that would mean that there is home court advantage. So there's an alternate way of stating our hypotheses in a little bit less technical terms. Okay. Now real briefly, let's talk about the calculations involved here. Like in section 5.7, we're going to calculate some expected values. Our data are observed values, so we're going to calculate expected values and compare the results. Now remember, the calculations of the test statistic are always done based on the assumption that the null hypothesis is a true statement. So if the null hypothesis is a true statement, that means that the result is independent of the location. So now, for instance, if we wanted to calculate the expected number of games that were a home and win out of a sample of 205, then we could take the probability of being home and win times the total number of games, which is 205. So this probability here we could think of as like the proportion of these games that we would expect to be a home win. Okay. Well, now if the null hypothesis were a true statement, then this event of playing at home and this event of winning would be independent. So based off ideas from chapter 1, if these ideas are or if these events are independent, then the probability of home and win would be equal to the probability of home times the probability of winning. Well, now using our information from our table here, we can estimate the values of those two probabilities. The probability of a home would be the total number of home games divided by the total number of games in our sample, 205. Likewise, the probability of a win would be approximately equal to the total number of wins divided by the total number of games. So there's an estimate of those two probabilities based off of our contingency table. And so now we can do this simple arithmetic here, and that comes out to be about 46.8. Okay? So if the null hypothesis were true, then in a sample of 205 games, we would expect about 47 to be a home and win. But what we actually observed was 55 home win games. And so now we can do similar calculations for all these different combinations, and we can write those expected results in a table like we have here. So here's the number that we just calculated. Here's the expected number of home losses, about 38. We can compare that to the observed number, which is 30. See, a little bit lower. Here's the expected number of away wins, 66. Compare that to the actual number, 58. That's a little bit lower. And then here we got about 54. That number was 62. And so what we have here is a bunch of observed values and their corresponding expected values. Now what we want to do is compare these overall observed results to these overall expected results. Well, that's just exactly what we did in section 5.7. And so we're going to do pretty much the exact same calculations as what we did in section 5.7. We're going to put all of our observed values here in a column, all of our expected values in a column, and then we're going to take each observed, subtract the expected, square it, divide it by the expected, and then add them up, and there's our test statistic, 5.391. So that's kind of a measure of the overall difference between these observed results and these expected results. If there's not a lot of difference, then this is going to be a small number. If there is a lot of difference, well, then this is going to be a large number. And so now we need to determine, well, is this a small value or is this a large value? Well, to answer that question, we rely on pretty much the exact same theory as from section 5.7. Theoretically, assuming the null hypothesis is a true statement, then this value C is an observed value of a random variable with a chi-squared distribution, and the number of degrees of freedom is a number of rows minus 1 times a number of columns minus 1, which in this case comes out to be just 1. So this has a chi-squared distribution with 1 degree of freedom. And then, like from section 5.7, the p-value is the area underneath the chi-squared density curve with 1 degree of freedom to the right of our test statistic. So this is always going to be a right-tailed test, just like in section 5.7. So the hypothesis test that we're doing here is called a chi-squared test of independence, or sometimes just a chi-squared test. And the basic purpose of a chi-squared test is to test if the row events of a contingency table are independent of the column events. And the generic null hypothesis is always going to be the statement that the rows are independent of the columns, and the alternative is going to be the statement that they are dependent. So that's always going to be the form of the hypotheses for this chi-squared test of independence. The requirements are, number one, that the data in the table represent frequency counts and are randomly selected, and all the expected frequencies are at least 5. So these are the same basic requirements as what we had for section 5.7. And one important thing to note here is that our data have to represent frequency counts. It means they have to be counts, they have to be whole numbers, they have to be counts of something that happened. They can't be measurements. Now, this test is a little bit easier to perform than our goodness of fit test from section 5.7, and that's because the calculator does all of the work. And this is going to work on both the TI-83s and the 84s. So the first thing we have to do is enter our observed frequencies as a matrix. We're not going to enter them as a list like we did in previous sections. We're going to enter them as a matrix. So the matrix menu is right above the X inverse key. So if you hit second X inverse, you're going to get a window that looks something like this. There's 3 submenus there. Go to the Edit submenu, and you'll see a list of all the different matrices. And you select the matrix where you want to enter the observed frequencies. We'll just choose the first one, matrix A. Now make sure that you go to the Edit submenu. I always make the mistake of going to the Names submenu, but we don't want that. We want the Edit submenu. So if you hit Enter, you'll see a window that looks something like this. First thing you have to do is enter the size of the matrix, which is number of rows times number of columns, 2 by 2, and then you just enter your observed frequencies from there. Okay. Next, you're going to go to the Stat Test menu and scroll up or down to option C, the chi-squared test. Now this option will be on all the calculators, 83s and the 84s. Now if you hit Enter, you're going to get a window that looks like this. It asks for two things, the observed and the expected. And so you need to enter the name of the matrix that contains the observed values. Now the default value should be A. If it's not, or you want to change the name of that, you can just go back to the matrix menu, and then under the Names submenu, select the name of the matrix that contains the observed values. Now next it asks for a matrix for the expected values. Now one important note here is that you do not need to calculate these expected frequencies. The calculator will calculate them automatically. All the calculator wants to know is where do you want to store those expected frequencies. And so we can just select any other matrix. The default should be B, and so we'll just keep that default. Now lastly, you've got two options, either calculate or draw. Select Calculate, press Enter, and you should get a window that looks like this. So first we see it's a chi-squared test, and here's the value of our test statistic, 5.39. That's identical to what we got by hand. And then here's the p-value, 0.02. And then here's the degrees of freedom. We see that's 1, the exact same thing we calculated. So for our purposes, the most important number here is the p-value, 0.02. Now we can interpret that p-value in the exact same way as every other p-value. We use the p-value to come to our technical conclusion. We compare that p-value to our significance level. None was given here, so we'll use the default 0.05. That p-value is indeed less than 0.05, and so our technical conclusion is to reject the null hypothesis. The last step in any hypothesis test is to state the final conclusion. So remember, the null hypothesis was the statement that result is independent of location. So if we reject that statement, that means that the result is not independent of location. So that means that there appears to be a relationship between the result and the location. So in even less technical terms, that means that the team does indeed appear to benefit from home court advantage. So there we go. That's all there is to this chi-square test of independence. It's relatively simple because the calculator does almost all the work for us. Now lastly, for fun, let's look back at our calculator, and we can look at the expected values. So if you go to the matrix menu and the edit menu, you see now that there's a size for matrix B at 2 by 2. And if you select Edit and press Enter, you can look at the expected value matrix, and that's identical to what we calculated by hand. So what could we do with these expected values? Well, what we've done is our hypothesis test tells us basically there is a difference between the observed values and the expected values. So now we could compare these expected values to the observed values and just kind of informally see where the differences occurs, and in what different combinations of location and result are there the biggest differences. Okay. Lastly, if we go back to our chi-square test window and select Draw instead of Calculate, you'll get a window that looks like this. And so what we have here at the bottom is our test statistic, and here's our p-value. And then here's a graph of the appropriate density curve. In this case, we have a chi-squared density curve with 1 degree of freedom. It looks like an exponential density curve, but it's actually a chi-squared with 1 degree. And then this is kind of hard to see here, but it will graph the test statistic and shade the area to the right, and that's our p-value. Now the test statistic actually goes off the window over here, so you really can't see that. But again, like all the other tests, the draw option just gives us a graphical representation of that p-value.